Now so far we have discussed about the thin lens formula, and the thin lens formula is your 1 by f is equal to 1 by v minus 1 by u, and this is true for a convex lens and also for a concave lens. And the expression for magnification is v by u, which is the height of the image to the height of the object, and this magnification is the linear magnification, or you can say this is the transverse magnification. Clear? Now by using this, again you can write this magnification, this linear magnification, in terms of v and f, image distance and focal length, and also object distance and focal length. So I can write magnification in terms of u and f. Magnification in terms of u and f. In terms of u and f. So how we find from this lens formula? From, it is true for all. From the lens formula, 1 by f equal to 1 by v minus 1 by u. Multiplying both sides by u, we have multiply u on both sides. U by f is equal to u by v minus 1. U by u, multiply both sides. So u by f is equal to u by v, v by u is equal to m. So u by v is equal to, I can write 1 by m minus 1. Or I can write 1 by m equal to u by f plus 1. Or this equal to u plus f by f. Or m is equal to f by f plus u. This is the expression in terms of f and u. So I can write this is equal to also f by f plus u. F by f plus u. Clear? Similarly, magnification in terms of, you can also find v and f. The simple thing is use the same lens formula. Next part, multiply both sides by v here. So I will get this expression as multiply v by f is equal to v by v is 1 minus v by u. So v by f is equal to 1 minus, what is my v by u? That is the magnification m. So m is equal to, take this side, 1 minus v by f. 1 minus v by f. So I can write this is equal to, m is equal to 1 minus v by f. So I can write this is equal to m equal to f minus v by f. F equal to f minus v by f. So this is the expression for the magnification in terms of f and v. So I can write this is equal to f minus v divided by f. Clear? So these are the expressions of magnification in terms of u and f, v and f. Now next we will discuss about the position and nature of the image formed by convex lens for different positions of object. I will place the object from infinity to the optical, center of the lens. I place the object. Clear? And if I place the object for different positions, where will the image form? And what will be its nature? Nature means generally we will say whether it is real or virtual. Next, whether it is erect or inverted. Next, whether it is magnified or diminished or of same size of the object. These three things we will find. And how from this formula? By using the lens formula, thin lens formula, and also magnification. By using that formula, how we will calculate. But in case of concave lens, no need to find any positions, because for a concave lens, wherever the object, we will get a image which is the image is diminished, virtual and erect. Virtual, erect and diminished. That we know for a concave lens. But for convex lens, we will find. So first position, suppose the object at infinity. Means here, position and nature of the image formed by the convex lens for different positions of object. Now the object at infinity. How we find where the image? So when the object is at infinity, I will take u is equal to minus infinity. Generally object distance is minus, it is on the left side. The object is placed left side. Then as you know, for a convex lens, the focal length is plus f using sign convention. Then I will find what is the v. That is the image. Use the formula 1 by f equal to 1 by v minus 1 by u. In that formula, 1 by v is equal to 1 by f plus 1 by u. So 1 by v is equal to 1 by f is plus f, and plus or minus whatever may be, minus infinity, 1 by minus infinity. So this will be 0. So no need to take this minus or plus, it is not matter here. So it is a minus infinity means 1 by infinity 0, minus 0, plus 0, same thing. So v is equal to f. I will get the image v is equal to f. Now you see, when I consider u is minus infinity means suppose this is the lens, the object is on the left side, I will get the image on the right side along the direction of right incident. Where? At focus. So image at focus. Image at focus. Now go for magnification. M is equal to v by u. Then what is your v? That is equal to f. And what is in u? That is your minus infinity. So this is equal to 0. Something by infinity is 0. Then magnification is the formula is h2 by h1, and the formula I am equal to. So h2 is equal to 0. Almost 0 means you can say whatever may be the height of the object, you will get 0 height of the image. 0 height of the image means the image, you can say that the image may be, we can consider that it is a real and inverted, because it is on one side, the other is on the, one is at the left side, the other will be on the right side, plus f. At the focus, real, inverted and diminished. Or you can say whatever may be the size of the object, you will get very small image. Now to draw the ray diagram. Convex lens, this is the aperture, you can say. Object is at infinity, so for infinity the image you will get, the rays should be parallel to the principal axis. These are the incident ray. After diffraction they will pass through the focus f, and this is the focal length, where this is the image, you can say v is equal to f, and u is equal to here minus infinity. So you get a point. Whatever may be the size of the object, you will get a point. Or also you can show this ray diagram also. Another way is that for an object, whatever may be the rays are always parallel. So let this is the focus. We always get, if a ray pass through the pole, for an object at infinity, we always get the parallel rays from the object, not necessarily for principal axis. If the object is on the principal axis and at infinity, you will get this type of parallel rays. But here also you can say this is another parallel ray. So after diffraction, it will go bends. After diffraction bends like this, it will bend. And these are formed at the focus. So this is the image at focus. You will get the image at focus. This also you can say u is equal to infinity, that is minus infinity. And here v is equal to f, that is the focal length. At focus you will get the image. Clear? So this is the case for object at infinity. Then the next case is the object is in between infinity and 2f. Object in between, the object in between infinity and 2f, double the focal length. So let u is equal to 3f. Focal length is 3f. Means it is object is in between f and 2f, or you can say object is beyond 2f. Then if it is beyond 2f, means it is greater than 2 the double times of the focal length. It is the focus double times of the focal length, beyond the double the length of focal length, and less than the infinity. Means it is not at infinity nor at 2f. It is in between infinity and 2f. So let me take u is equal to at a position minus 3f. Then as you know f is equal to plus f. Then you will find 1 by f equal to 1 by v minus 1 by u. Using that formula, 1 by v is equal to 1 by f plus 1 by u. So you can put 1 by f minus 1 by 3f. Because this is plus or minus, minus 1 by v. So 1 by v is equal to, I can say 3f. Then if you take f, 3 minus 1. So 1 by v is equal to 2 by 3f, or v is equal to, I can say 3f by 2. Means it is what? 1.5f. 1.5f. The image will be at 1.5f. Now you see here, object is on the left, image is positive. V is equal to 1.5f or 3f by 2. So the image is in between, I can say it is in between f and 2f. Here, next, go for magnification. M is equal to h2 by h1, which is equal to v by u. So I can say h2 by h1. What is v? Already I got v is equal to 3f by 2. What is u? U I have taken minus 3f. Take this sign convention. So this 3f get cancelled. So h2 by h1 is equal to minus half. Minus half. So h2 is equal to minus h1 by 2. What it means? h2 is equal to minus h1 by 2. Then as you see here, what is the height of h1? h2 is half of this one. Means you can say it is diminished. Diminished. Next, if it is plus h1, this is minus. h1 is plus, then h2 is minus of this. Means if it is above, h1 is above the principal axis, the image will be below. So you can say below means diminished and inverted. And obviously this should be a real image. Means one is on one side left and the other is on the other side. So we can say these are the cases we can find. Then to show the ray diagram, here let this is f and this is 2f, and this is a position suppose 3f. So this is 3 times of focal length. Let the object is here. Now take the ray 1 here. So let this is the focus. The ray will bend like this. Clear? Another at the pore, incident the pore. It goes undeviated. These two rays will meet at this point, and this will be the image. Okay? AB is the object, and this is A dash. B dash is the image, which is diminished, inverted, and real. So this is the image position. is the smaller the object size. Clear? So this is the case. And where it will fall? Suppose this is your f and there will be your 2f. It is in between f and 2f. In between f and 2f. Clear? Next. Third case is the object at 2f. Now take the object at 2f. At 2f. Third case at 2f. U is equal to minus 2 to the focal length. Object distance is negative. Focal length is positive. F 1 by v. I am putting direct 1 by v is equal to 1 by f plus 1 by u. So 1 by v is equal to 1 by f minus 1 by 2f. 1 by v is equal to 2f. 2 minus 1, that is equal to 1 by 2f. So v is equal to 2f. Object is at 2f on one side, image will be on the other side. It is plus, it is minus. So we can say at image at 2f, 2 times of the focus 2f, and also real. One is other one side, the other is on the other side. M is equal to h2 by h1, which is equal to v by u. So h2 by h1 is equal to v is what? 2f. U is what? Minus 2f. So h2 by h1 is equal to minus 1. So h2 is equal to minus h1. One is plus, the other one is minus. So it is inverted and same size, no change. Size is same. Same size of the object. Same size of the object. So now keeping the object from infinity to 2f. So let this is your f. Let this is 2f. Now this is the object. So you will get. So let this is an f. So the ray will pass through f. And then through this one, optical center. And it will meet at this point, which should be equal to what? So this should be of same size, so make the same size also. Clear? So this is one portion, the other one is of the same size. Clear? This is 2f. So AB is the object and A dash, B dash is the image. Both are at 2f, same size, inverted. Right? From that calculation, you can know the nature and positions. Okay. Then the next part is when the object is in between f and 2f. In between f and 2f. Object is in between f and 2f. So in between f and 2f means, let me take the object is in between f and 2f means, let me take u is equal to more than the 1 time focal length, less than 2 times focal length. So let me take a focal length of 3 by 2f minus 3 by 2f. It is greater than capital small f, less than 2f. U is equal to this one. And f is obviously positive for a convex length. So 1 by v is equal to 1 by f plus 1 by u. 1 by f minus 1 by u means this I can write 2 by 3f. So this equal to 3f. Take this 3 minus 2. This is equal to 1 by 3f, which is equal to 1 by v. So v is equal to 3f. So it is negative, this is positive. And 3f means beyond 2f, on other side. Image at 3f means we can say beyond 2f. Beyond 2f. And it should be real. The image should be real because one is negative, the other one is positive. So it is a real. From here we got this one. Then for magnification, m is equal to h2 by h1, which is equal to what? V by u. So h2 by h1 is equal to, what is V? 3f. Then u is what? Minus 3f by 2. So this cancel. h2 by h1 is equal to minus 2. Minus 2. So h2 is equal to minus 2h1. One is plus, the other is minus 2h1. h1 is plus means h2 is negative. Minus 2 times. So it is what? Magnified. Magnified. How many times magnified? 2 times. Magnified. And plus minus means what? Inverted. And inverted. So we can find the ray diagram like this. So for the object f and 2f, unit f and 2f. Clear? So this is your f on this side, let this is your 2f, and let there is a 3f, and the object will be like this between f 2f and 3f, means image at 3f. So we can say, so this is the 3f position at 3f, means beyond 2f the image will be formed. Clear? Then now we will go for the focus. If the object is at focus, when the object is at focus, then what we will get? At f. At f. At focus. F. Clear? One is at f. So u is equal to what? Minus f. And focal length is always, f is always positive. 1 by v is equal to 1 by f plus 1 by u. 1 by v is equal to 1 by f minus 1 by f, u is equal to minus f. So 1 by v is equal to 1 by f minus 1 by f get cancel, 0. So v is equal to infinity. Image at infinity. At infinity. Clear? So if you go for magnification, m is equal to v by u. So v is equal to infinity divided by u is what? Minus f. Infinity something is infinity. Means h2 by h1 is equal to infinity. So h2 is equal to infinity. Clear? Then you will get the lens is like this. It is the focus. If the object is at the focus, from the lens, it will go like this. Here it is the focus, and the another ray, it will go what? Parallel. These two rays will go parallel. They will meet at infinity at focus. So very large image is what? Very large image, and at infinity. And real and inverted, because the image will form on this side. Real and inverted. They will be at infinity. So that infinity means object is this side. Image you will get on this side, but at infinity. You will not find the image, but the image will be there. Clear? So this is the case. Then between f and optical center O, if the object is between focus and optical center, then you will get the image virtual convex lens. Virtual, magnified and erect. That we have done in the one of the case where the derivation, we use the derivation for the lens formula. Where we derive the lens formula by using object in between optical center and focus. I place the object here. I got the image in this position, magnified, virtual and erect. That is the special case. So these are the different cases of for position of the image, for different position of object for a concave lens. And for a concave lens, we already know that it always produces a virtual image which is erect and diminished. And remember one thing, all the real images are inverted. Virtual images are erect. Because wherever you get a real, you can write blind. It is inverted. Then you will get a virtual image, it will always erect. Clear? Now, next is the very important topic. Generally, we use our day-to-day life, the power of a lens. When you are asking to your friend or when you are talking with someone else, when he is using a spectacle, then for correcting his eyesight, we are asking him or her that what is your power? What is the power of the lenses you are using? Clear? So we are using the term power. So what actually the power means? What is the power means? Power of the lens means. We can say the power of the lens is the ability of the lens to converge or diverge a light beam falling on it. So we can say the ability of a lens, the ability of a lens to converge or diverge, a beam of light, falling on it. Suppose a beam of light, a number of rays, collection of rays is called as a beam. Suppose so many number of rays are incident on the lens, maybe a simple example here, double convex lens or double concave lens, and the rays are incident, then how much the lens converge or diverge, means you can say how much the lens or the ability, or you can say the strength of the lens, how much it can deviate its path, its original path. As you know, when the ray is incident and it passes through the lens refraction occurs, and the refraction, due to refraction, the ray will bend. And how much it bend the ray, that actually we are measuring, and that is called as your power. And this converge and diverge, converge means it is a converging lens, diverge means diverging lens, means it is for the convex lens, it is for concave lens. That's why we are using the converge or diverging. So we can say the strength of a lens, the power of the strength of the lens is the measure of its ability to deviate, the path of light rays. It is the measure, we can say also, measure of the ability to deviate the path of light ray. Measure of the ability to deviate the path of light ray. Okay, passing through it. Passing through, obviously that ray should be passing through the lens, passing through it, passing through the lens. Now you see here another definition, that is the most definition that is for mathematical purpose. We use another definition, that after I deriving the formula for power, then I will go for that definition, derivation. And remember one point is here, very very important point, that the smaller the focal length of a lens, more is its ability. Smaller the focal length, smaller the focal length of a lens, more is its ability to deviate. More is the ability to deviate the rays of light. Rays of light incident upon it. Incident upon it. Okay? More is its ability to deviate the rays of light incident upon it, or you can say more is its power. This is nothing but your called as the power. So smaller the focal length, more is the power. Now you see how it converts or diverges. Now we find the formula for power of a lens. Okay, and generally it is shown by a capital letter. We can say P. The power can be shown by a capital letter P. So let us consider a convex lens, right? And let this is the principal axis. Clear? Let us consider a ray incident parallel from the principal axis, parallel to the principal axis, incident on the lens. If there is no refraction, no lens, then this is the actual path. The ray will go parallel. If there is no refraction, vector linear propagation, if it is incident parallel, so it will go parallel. But because of refraction, what will happen? As you know, because of refraction, the ray will bend, and as you know, it is incident parallel, then the ray will be at point focus. Then how much it deviates? This angle delta. From its actual path, it deviates an angle of how much? Delta. Here, this is the deviation delta. Right? And let us consider this is the optical center O, and let this is the point A, and this is your F. Then if it is delta, then obviously this line two are parallel, so this will be also delta. These are the two parallels, delta. And this is always perpendicular. So that is the case. How much it deviates from its path? Delta. This is the measure to know the power of a lens. We measure this thing. But how? What we measure here? Now you see here in this case, in this figure, in the triangle OAF, in the triangle OAF, here the ray is what? Converges. So if you take another parallel ray, it converges. In the triangle OAF, what is tan delta? Tan delta is equal to OA by OF. Let this OA is at a height h. So I can write this h, and OF is obviously the focal length. So f. Clear? Tan delta is equal to h by f. Clear? Then if h is equal to 1, if h is equal to 1 unit, then tan delta is equal to 1 by f. This tan delta is nothing but called as your power, which is equal to 1 by f. This is called as the power of the lens, and it is the converging. This is called as your power of the lens. Okay, and remember this power of the lens, how we will define this? It is the tangent. So the power can be defined as the power of the lens is also defined as the power of the lens. Power of the lens is defined as the tangent. Means tan. The power of the lens is defined as the tangent of the angle by which tangent of the angle by which it converges or diverges. It converges. Here we are going for converges or diverge. I will show for the diverge case also. Converges or diverges. How much it converges or the diverges? A beam of light falling at what? Unit distance. At unit distance from the optical center. Clear? So this is for convergent. And already I told that smaller is the focal length. If the focal length is here, more will be the bending. So in the power of a lens, I have defined that. I have told that smaller is the focal length, more is the bending or diverging. Because if the focus comes here, then as you know, a ray incident parallel, it will always pass through focus, to this focus. So there is more bending. So delta is more, the power will be more. Smaller is the focal length, more is the ability to diverge or converge. Here it is converging. For diverging case, that is for diverging lens. For diverging case also you can take, for diverging, right? The diverging lens, concave lens, the center. Let us consider a parallel beam. If there is no refraction, the ray will go parallel. But because of refraction, what happens? The ray diverges from its axial path. So it diverges like this. How much diverges? Delta. That we are measuring. And if you proceed like that, where it will meet? You meet at the focus F. Let this is your O, optical center, and let this is your A, right? And if this angle is delta, then what about this angle? Delta. This will be also delta, right? So delta means phi, because this angle is delta, so this will be also opposite angle delta. These are parallel, delta. Then again on the triangle OF, like that, O is equal to X and OF is equal to F. But remember, this is the power. But when you calculate this, when you use the sign convention, here this focal length, the light is incident and you are measuring the distance opposite. For a concave, already you know that for a concave lens, its focal length is negative, so its power will be negative. And for a convex lens, focal length is positive, so power will be positive. So from here we got the formula for power. Remember this formula. The power of a lens is the reciprocal. Power of the lens is the reciprocal of focal length. And remember, F should be in meter. F should be in a meter. And the power, if F is in meter, then the unit SI unit of power is 1 diopter. It's the SI unit of power is diopter. It is the diopter. Here, this is the SI unit diopter, or you can say D. That the SI unit. Or you can say P is equal to, if F is in centimeter, 100 by F in centimeter. Same formula. Remember, if focal length is given in meter, then power 1 by F, that is in diopter. If it is in centimeter, 100 by F in centimeter, then the unit is same diopter. So 100 by F if F is in a centimeter. Clear? That is the diopter. And another thing is that for convex lens, F is positive, so P is positive. For concave lens, F is negative, so P is negative. P is negative. Power is negative. Clear? That is another concept. Then now you can say that the power of the lens, as you know from the lens maker formula, 1 by F lens maker formula, mu minus 1 into 1 by R1 minus 1 by R2. Now I can write this lens maker formula as 1 by F is equal to, now the formula is power. Power is equal to mu minus 1, refractive index of the material of the lens, and the surrounding is air. Or you can take mu to 1, relative. You can take the formula 1 by R1 minus 1 by R2. So power equal to mu minus 1 into this much. And remember one here thing is that the power, in this case, the power of the lens is directly proportional to the refractive index of the material of the lens. And as you know, the refractive index is proportional to, according to Cauchy's formula, inversely proportional to lambda square. That is inversely proportional to lambda square. So if I will ask you a question, plot a graph between the power and lambda. Then power and lambda is how much related? It is inversely proportional to lambda square. power is inversely proportional to lambda square. So we will get a relation like this, P and lambda. This is a graph between power and lambda. It is power is inversely proportional to the wavelength of light incident. Clear? So this is the all about the concept of power. Clear? Another topic is combination of thin lenses. Generally what happens in different optical instruments for different purposes, to get more magnification, or you can say to get a erect image of an object or to get a sharp image, we use more number of lenses and combine together. They placed nearby. So that is the combination of lenses. Okay. So we can say in the optical instruments we are using to magnify. We are using number of lenses to magnify the image or to increase the sharpness of the image. Okay. And or you can say to increase the field of view of the image. So if the magnifications produced by each lens is M1, M2, M3 like that. These are the number of lenses, thin lenses, whose magnifications are M1, M2, M3 linear magnifications like that. Then when you combine that thin lenses, the total magnification due to combination, the total magnification always, remember the total magnification M is equal to is the product of magnification produced by individual one. Product of magnifications produced by individual ones. So this is the magnifications. Okay. Then total magnification by the combination of thin lens. Then from here we will get equivalent lenses. From here we will get equivalent lenses. So what is this equivalent lens or equivalent lens? What is an equivalent lens? Suppose we have a number of lenses and we are using the number of lenses such that the number of lenses combined together give us a final image at a point due to an object. Now if I replace all the combination of lenses and I will place another lens such that if the object is same and the image is same for that single lens, then that single lens is called as the equivalent lens of the combination of lenses. So we can say a single lens which forms the image, a single lens which forms the image, a single lens which forms the image, of an object at the same position, of an object at the same position as if formed by combination of lenses, okay, is called a equivalent lens. Is called equivalent lens. But if I am using a number of lenses, their focal lengths obviously different, f1, f2, f3 dot, and I am using a single another lens, its focal length should be obviously different. So how I will relate the focal length of the individual lenses with the equivalent lens focal length? That is the formula I will find. Okay. Now equivalent focal length. Now next we will find out the equivalent focal length. Equivalent focal length of the combination of two lenses. First I will find for two lenses, then we will go for number of. Equivalent focal length of the combination of two lenses. Equivalent focal length of two thin lenses. First I will find equivalent focal length. Then I draw the ray diagram, then you can understand the concept done. Let us consider a lens L1. This is one lens L1. Its focal length is f1. And there is another lens, suppose L2, is in contact with this one. These two are in contact. L2 is another lens which are in a contact. Here they are in a contact. And obviously this is the picture and this is the aperture of this one. And let they are placed coaxial, means on a common principal axis. They are placed on a common principal axis. This is the optical center of this one, O1, and this is the optical center, O2. O1 and O2 are the optical centers. Here O1 and O2. Lens L1 and L2. It has a focal length f1 and this has a focal length f2. So let us consider, for this case, let us consider an object O is placed at this point. Because of the lens L1, what happens now? You see, another ray goes incident, right? A ray incident like this. If this lens is not there, L2 is not there, then obviously the ray will go what? The ray will go, refraction occurs, and the ray will be at this point. And another ray like this, these are the two rays, they meet at this point. Let this is the image I1 by the lens L1. But because of the second lens L2, what happens then? Because of the second lens L2, here again that refracted, when it passes through this lens, the incident ray, this is the refracted ray, when it passes through this lens, again it bends further like that, and you will get the image I here. Actual image is I here. Whole concept is that let this is the object distance U and let this is the final image B and let this is the image B dash I1. I1 is let here B dash. Clear? So all the distance generally we are measuring not from here. You can say we are measuring the distance from here also. We can take the distance like that from the center of these two. Clear? These are the distances like that. Now for the lens L1, O is the object position, I1 is the image. But for lens L2, if the lens L2 is present there, double refraction occurs, so that for the lens L2, I1 is a virtual object and I is the real image for L2. That is the case. Clear? So this is the refraction. Because of the lens L1, O is the object and you will get the image I1. But because of the second lens, I will find the final image at I. So if I replace these two lenses, by another lens like that, I show like that, I will use a lens like this. This is another lens. I am using a lens like this and this is L, whose focal length is suppose F. Then what is the relation between this F and F1 and F2? Like here, now I will find out using the first case. So these are the two lenses. So for the lens L1, for lens L1, O is the object distance. Sorry, O is the object and I dash I1 is the image. Lens formula, using lens formula, thin lens formula, using lens formula. If its focal length is f1, 1 by f1 is equal to 1 by v1, b or b dash or v1 you can say, 1 by v1 minus 1 by u. For lens L2, that is most important, I1 is the virtual object The object is not there. But because of that, when you see the image, you will find that this image comes from an object placed here. So this is an object for this lens. So virtual object and I1 is the virtual object and I is the real image. Positions. These are the positions. So for that, using the lens formula, here also using the lens formula, what I will get? Its focal length 1 by f2 is equal to, what is your object distance? So first image distance, b minus object distance is what? 1 by v1. Here. Now, replace these two lenses. Here. Now, replace these two lenses by another lens L whose focal length is f and O is the object and image is I. Now I replace these two, I place a lens L whose focal length is f, object is O and image is I. Right? Then, okay, let me add these two. Adding these two, first add these two. 1 by f1 plus 1 by f2. 1 by f1 is equal to what? 1 by v, sorry, 1 by v1 minus 1 by u minus, for 1 by f2 is what? What is the formula for 1 by f2? 1 by minus 1 by v, which is what by, sorry, 1 by v1, so minus plus 1 by b minus 1 by v1. Clear? So this will cancel each other. 1 by f1 plus 1 by f2 is equal to 1 by v minus 1 by u. That is the combination of these two. Clear? 1 by v minus 1 by u. Clear? For the combination of the thin lenses, let a lens L is of focal length f replace let a lens L of focal length f replace the two lenses and O is the object and I is the image. Replace this, use a lens L. Then the lens formula 1 by f is equal to 1 by v, final is v minus 1 by u. Compare these two equations. Comparing 1 and 2. Now I will erase this thing. Comparing equation 1 and 2. Comparing equations 1 and 2. What do we get? 1 by f equal to 1 by f1 plus 1 by f2. This is for two lenses. Clear? Or f is equal to the equivalent focal length is equal to f1 f2 by f1 plus f2 for two lenses. For n lenses, the equivalent focal length, focal length 1 by f equal to 1 by f1 plus 1 by f2 plus 1 by f3, like that. You will get the equivalent focal length. Then from here also you can get the equivalent power from formula. Then what is the equivalent power? So this is the equivalent focal length of two thin lenses. This is the formula. Equivalent power. What will be the formula for equivalent power? Equivalent power. What will take? 1 by f equal to total equivalent power. 1 by f1 is the power of the first one, second one, plus third one. Like that, the powers are combined. Right? This is the equivalent power. Here, then after getting these powers and all these things, now we got the formula for lenses. Now, in these same cases, if you have given one is a convex lens and the other one is a concave lens like that. They are placed like this. It has a focal length f1, it has a focal length f2. Then when you calculate the equivalent power, one is convex, the other is concave. So as you know, use the same formula 1 by f equal to 1 by f1, it is positive, then plus 1 by, what is the focal length of the concave? Minus f2. You will put it minus f2. So formula is same. So 1 by f equal to what you will write? Minus 1 by f2. That is the combination of a convex and concave lens. That is the formula for equivalent focal length. Then after that calculation, you can find out if the two lenses, remember this formula also, if the two lenses, convex lens and another convex lens of different focal length, lens L1 and L2, it has a focal length f1, it has a focal length f2, and they are separated by a distance d, optical centers O1 and A2, and they are coaxial. If they are placed like that, separated by a small distance d, then in that case, remember this formula also, the equivalent focal length is equal to, for this case, 1 by f is equal to 1 by f1 plus 1 by f2 minus d by f1 into f2. You can derive that, derivation is not required, but the formula is very, very important, minus d by f1 into f2. And if you write in terms of power, then I can write in terms of power, equivalent power P is equal to, this is the power of first one P1 plus P2, let this be 1 by F1, P1 into P2. This is the form of power, equivalent power, if the lenses are separated by a small distance d. Clear? So these are all about your refraction chapter and refraction through a thin lens. Clear? This is about refraction by a lens, and this finishes your lens topic. Okay, and go through the notes and the materials, then you get again more clear idea, then you can write the notes also from there. Clear? Thank you.